But let's finish this, the next property, or it's a property, but it's a separate section. Talk about this convolution. I just get a few minutes left. So let's maybe just get to the form of the convolution. And it's actually very similar to the Fourier transform convolution. Basically, it's like doing an inverse transform of two transforms. So you have two transform f sub 1 is Laplace transform of capital F sub 1. And then F sub 2 is Laplace transform of F sub 2 after F sub 2. Now you want to do the combined product of this transform. And remember, in a Fourier transform, you multiply by 2 Fourier transform, that the inverse transform is a convolution. Now you want to see what the inverse transform of the product of two Laplace transform. Okay, and so obviously the expectation would be similar. Right? But the form of convolution looks like a little bit different, but it's actually exactly the same. If you, I mean, other than we defined the Laplace transform a little different from Fourier transform from the beginning. From the beginning, for Fourier transform, you use a symmetric definition. So you have square root of 2 pi on transform, the inverse transform. But in Laplace transform, we already defined one without the 1 over 2 pi, like the transform we defined without the 1 over 2 pi. So that show up in the definition of the convolution also. So other than that, it actually the same. Now we go on to that. So you just basically multiply, applying the formula. So F sub 1 is 0 to infinity minus ST, F sub 1 T, and E sub 2 is 0 to infinity. Actually, the textbook changed it, but this first one you use this X. Oh, yeah, I forgot the dx. So that's the F sub 1. F sub 2 is similarly using Y, Ty, and Dy. Now the idea is you combine the two exponential first. Infinity e to the minus s x plus y, and I mean up to here is that's just like nothing, but we want to get the other integration also, like dy though, dy. So you have f1 x, right, and f2y dx dy. Right. The reason to do that is we want to redefine your variable. So if x plus y defined as t, this is defined as t, and later on we keep the dy, but change x. So x plus y is t, so x is t minus y, right? And dx, this is y, t minus y, but dx we want to change also. Dx is just dt. Okay, so you rewrite that. Infinity e to the minus st, and f sub 1 t, f sub 2 y. I mean, not t minus y, f sub t minus 1, f sub 2 y, and you have the dt dy. Actually, I didn't actually need to take it out. But anyway, so now we reverse it. Let's just reverse that order. So this is just we define your. Wait, I probably make something I not too careful enough. So when you take the variable, change the variable, when the original x is from 0 to infinity, right? Now you change it to t minus y, right? So when x, so do you want to figure out the t limit? The t limit is t. But t limit is also 0 to infinity. You basically, if you have x and y, 0, x plus y is just and constant along the diagonal line, right? So t is, this is t, and from the original integration area is this area, right? And now t is still from 0 to infinity. So this limit of t is okay. The t is 0 to infinity, but y need to change, right? So y is this in so for a given t, so y is from, so this is your new variable. You change it. Is the x and y, you change it to t. So for a given t, so for say like this line t, right? Originally is x, right? So you the y is integrating from, you don't integrate from the infinity. That maybe a little explanation. The y is need to change to just integrating from 0 to t, right? It's like this area. Basically, it's 0 to t. Interchanging that 0 to t, and I probably need to explain a little bit more next time because I'm running out of time. But if you call that as a function, because this is dy, call this as function, dt, and that is what we define as a convolution. Right, that is a convolution. This is defined at f1, just the same symbol, right? And this becomes a Laplace transform of f1 f2 convolution. But anyway, I'm just coming, but this little a little bit more explanation. I'm just running out of time to explain that. Okay, but we'll come back to that next time. Okay. Now we're in the Laplace convolution. It's similar. It's actually, you can put it in the same form like last time I mentioned that. But I was running out of time, so I don't know the last point that we tried. I tried to. I just wrote down the definition of convolution in Laplace convolution, but there was one transform change of variable that involved changing the integration limit that I may not have explained, or you may not understand. I mean, that could be trivial for someone, but then if you are not too familiar with change of variable, you might have trouble. So you have a f1s, f2s, and last time what we derived is that this is a Laplace transform of a convolution of integral c to t. That is might be trouble. So f1 is the function that corresponds to the Laplace transform of capital F1 will give you F1. And that is, we use t minus, and the F2, right? F2, the Laplace transform of capital F2 give you little F2, right? And then integrate. So this is the form similar to the Fourier convolution, so except that's the limit, and then also the normalization. We are using different convention now, so we don't have this square root of 2 pi in the definition. But this change of limit instead of 0 to infinity is coming from the change of variable. Originally, when you do define the Laplace transform, each one is integrating like f sub 1 and f sub 2. From one is x, the other is y, so 0 to infinity, basically integrating over this space, this area, right? Or you can originally just the grid is like that, integrating x and y is like a Cartesian coordinate, although it's just functional space. Both should be a time. I mean, if this function a function of time, both are actually represent time variable. But you draw it like that. This is like a Cartesian coordinate. Integrate over this area. So, for a fixed x, whatever x value, you integrate from 0 to y. But now we do a change of variable called t equals to x plus 1. It means that now you change your coordinate line. Right? So you keep y, but you get rid of x, but you use the t variable. So t is x plus y, meaning that t is constant, means that it's a line that is diagonal with a slope of -1. Right, in this space, this is t equals x plus 1. Right, and then the y coordinate line. So all the coordinate line of t, constant t, are like that diagonal line. Right? But you also keep the y coordinate line, right? And now for a constant t, for any given constant t, so this is t, right? This value is t. Then you don't integrate y from 0 to infinity. You integrate only from 0 to up to this point. And this point is the intersection of this line with y, which is y. This is intersection at the y-axis, which is x is 0. So this value is y equals to t. This is y at this point, right? To integrate for a given t, you integrate just from 0 to t, right? Instead of 0 to infinity. It's okay. So that is how you get this 0 to t, right? Is it clear here? Yeah. So that is just from the change of variable, right? So but I also said that you actually this one actually you can make it similar to the Fourier convolution. The form is exactly the same. If you recognize that f1 and f2 both are function that's 0 for a negative argument. If the argument becomes 0, the argument is negative, then the function is negative. Or you can say that it's you can multiply by a beta function. So you can we define f1 or you can say that's a f1 is this f1s is the Laplace transform of f1. This is function of t, but multiplied by a step function t. Right, the step function we define step function is 0 for negative argument. So this is t, and the t is 0. It's 0 for negative t, 1 for positive t. Right, this is a step function. Right, so and we can always do that because the Laplace transform involves this integration the positive t, right? So multiplied by a theta function doesn't matter, right? So it's still the same. And likewise, f2 will be, you can define multiply as a step function also, right? And then we can obviously see that this convolution is f2, which is this one defined as this one. It's just the same as unlimited. So minus 1, 2, 3, y, 2. It's, if you multiply by the step function, we expect the two step function to f1 and f2 respectively, like that. And you can extend it from minus infinity to infinity, and this will give you exactly the same result, because you can check that, right? Because for negative y, you integrate over y, right? For negative y, then the theta function here will make the integral 0, right? This is a theta function of theta y, so it will get rid of all the negative y. So although you integrate from minus infinity to infinity, all the negative value actually is 0 integral. So you can just effectively this lower limit change back to 0, right? And then the upper limit, you can look at this function, this step function. Now y is all positive, right? And so if you integrate y is greater than t, if y is greater than t, that argument becomes negative, right? And this argument is negative, meaning the integral is 0. So effectively, the upper limit is only at t. Okay, so you multiply with respective step function, just like what we did here. Just redefine your f sub 1, f sub 2, the function in time domain. Then you have the explicit step function. Then you can just integrate from unlimited range of the integration variable. It's just effectively the same. Is that okay? So, the two convolution, Fourier convolution and Laplace transform can be made very similar if you include the step function in your definition of your original function. Is that okay? So that one way to just make it similar, and also this might help you if you forget about how you change this limit. And think about this f1 and f2. They are only non-zero for positive argument. Then you can figure out that the range should be 0 to t. Okay.